All right, chapter 9, attractive forces, things like being tall, having charisma, having lots, oh wait, sorry, wrong attractive forces. This is attractive forces for things like molecules, atoms. So there's forces that exist between molecules. Those are the intermolecular forces. So the inter part between and the molecular, right, molecules. So forces that exist, interactions between molecules. There's a bunch of them. There's 4 that we'll talk about, 3 that are kind of in one group, and then a 4th one that exists under some circumstances as well. The interactions between molecules in coffee that taste bitter and other foods, right? All of those have different effects on certain receptors in our mouth, and those effects, the way that we interpret those tastes, are determined by the forces that exist between the molecules in what we're eating or drinking or smelling and the taste buds in our mouth. We need intermolecular forces to live. If there were no intermolecular forces, then we would all just be scattered dust clouds. Just atoms floating around by themselves or molecules floating around by themselves. It would all be gas. There are some not specific intermolecular forces, some general, some vague, weak intermolecular forces that exist between all molecules and atoms. And it's due to intermolecular forces that liquids and solids exist. Intermolecular forces, the strength of intermolecular forces, how sticky they are, essentially, or alternatively, how magnetic they are, another way to think of it, determines the state, solid, liquid, or gas, of a substance at room temperature. And there's not like a direct correlation between it has these intermolecular forces, so it's going to be this state at room temperature, but we can make predictions about boiling point, melting point, and possibly about what sort of state those atoms and molecules are going to be in if we know their intermolecular forces. Things that have strong intermolecular forces, things that stick together really well, that hit each other and don't bounce off immediately, tend to result in liquids and solids. Things that are touchingly close. They're more difficult to separate because they're stickier with each other. They have stickier interactions. This might be like if you were walking around Costco randomly and you bump into an old friend from high school who you haven't seen in a while. You might you're walking around through all these people, not having any interactions with them. Suddenly you run into a friend and then you realize you've been chatting for 30 minutes in the snack aisle and you haven't even been looking at the yummy snacks that are around you. If you have weak intermolecular forces, and by you I mean molecules, if molecules have weak intermolecular forces, that's the random strangers in the Costco. You're not going to really interact with them. You might bump into them, but more likely it's just, oh, hey, sorry, and then you're on your way again. So weak intermolecular forces, these are not going to stick together. Or at least not strongly. You can get them to stick together for most things, possibly all things, but it's very easy to overcome those attractive forces, and so they're going to separate with relatively low amounts of energy. Our firstest force is the dispersion force, also called the London force, also called the London dispersion force. Dispersion forces are our weakest force, our weakest intermolecular force. This is the default, the basic intermolecular force. Everything has dispersion forces, with some minor caveats that aren't really important, but things that don't have electrons don't have dispersion forces. So dispersion forces are caused by fluctuations in the electron distributions. Electrons, we can think of it, are always moving. So we've got our model of an atom, and let's think of it as just having one little cloud of electrons, right? The electron, or however many electrons there are, could all be on one side or the other, or they could be evenly distributed. And those changes, that jumping around of the electron, might cause there to be more electrons in one area, more electrons on one side of the atom versus the other. So we'll get a partial negative versus a partial positive. We'll see pictures of that on the next slide. But the idea is that for a moment, just a moment, there could be a fluctuation of electrons that causes us to have partial positive, partial negative. So we're looking at helium atoms here. They'll have 2 electrons. Do we have another one of these? We don't. Great. So at a given moment, this is our nucleus in the middle, our electrons might be evenly distributed, one on either side. In another moment, like this middle, these electrons could both be on the left side. Oh, don't make it bigger. Just randomly, for the tiniest fraction of a moment, a shorter time scale than you can comprehend, those electrons might be just over on one side. And since we have electrons over on the left side, the electrons are negatively charged, and we don't have anything on the right side getting in the way of the positive charge of the nucleus, and so we'll get a partial positive charge making its way through to the right side. And that will happen for, again, the tiniest, shortest little moment that you can possibly imagine, and then cut that in half a couple dozen times, and then it's like that time scale. So for a moment it's there, and then it might be gone, and then it's back, and then it's gone, and then it's gone, and then it's back, and it's back, and it's so back, and then it's gone again, right? So it's happening constantly, but for very, very short periods of time, and it's also just a partial negative, partial positive, and it depends on like how many electrons have all gotten over to one side versus being evenly distributed. But what this can do is that if we have this happen on atom A, and it's next to another atom of helium, this partial positive from our nucleus can pull the electrons from our other thing over to it. So it can induce or cause to happen, can pull those electrons over from its neighbor for a moment, a tiny little moment, the shortest moment you can possibly imagine. On average, the electrons are going to be evenly distributed, but for little snippets of time, they're sticky because of this pulling force of the electrons between the different atoms. Very weak and short-lived force. So this slide is just saying what I was talking about on the previous slide. If we get this instantaneous dipole on one atom, then this partial positive can pull the electrons from the neighboring atom. And so then that can cause a partial negative and partial positive in the nearby helium atom, and then these positives and negatives sort of pull them together, again, very weakly and only for a short period of time, and then they'll separate again. But since this is just based on electrons and where they're located at any given moment, anything that has electrons can have this force. So they're constantly appearing, the forces, that is, and disappearing. Just based on where the electrons happen to be. Some factors that play a role in how strong the dispersion force is. So the magnitude or strength of those dispersion forces depends on the electrons in the atom. If they can easily be pulled over, they can easily be moved around, then it's going to be easier to induce that partial positive, partial negative charge. A larger electron cloud is more easily polarized. More electrons means stronger dispersion force. It's not the only factor that plays into dispersion forces, but it is an important one, and if we're looking at a similar family or group of atoms or molecules, then we can make comparisons based on molar mass. Because higher molar mass or larger molar mass means more electrons. Again, this only works if we're talking about similar elements or compounds. So this comparison works for things like noble gases and hydrocarbons. Things that are just hydrogen and carbon. Like CH4 or C2H6. So let's look at the effect of differences in dispersion force strength. We're going to compare noble gases. So here's our noble gases. We've got them arranged in the order that they show up on the periodic table. So helium's our smallest. It's all the way up at the top. And then moving down to xenon as our lowest that we'll be looking at here. So we've got them arranged by molar mass. We increase the molar mass as we're moving down this table. And we've also got their boiling points in kelvins. So smaller number, right, lower boiling point. And helium has a boiling point of 4 Kelvin, which is very cold. And xenon has a boiling point of 165 Kelvin, which is still very cold, but it's a lot warmer. 165 Kelvin is like minus 110 Celsius. Boiling point is sort of. It's related to intermolecular force strength. It's proportional, sort of. So when we're saying that we've got really low boiling point, it means that It takes very little energy for those atoms to not be stuck together anymore as a liquid. So our boiling point is the temperature that atoms don't touch each other anymore, or can. What am I saying here? Temperature that atoms separate. The intermolecular forces are beaten, overcome. So IMF, they're standing for intermolecular forces, not International Monetary Fund. So helium having just 2 electrons can't get very strong dispersion forces. You can only move around 2 electrons. It's also less easy to move them around, on top of there just not being as many for there to be strong forces. Xenon, on the other hand, has 54 electrons. And so it's much easier for you to pull some of those electrons over. We also have increasing atomic size, since we've got our electrons basically in shells and layers. So it's those electrons on the outside are going to be easier to pull over to one side or the other, since they're not as close to our nucleus. So it's a little easier to influence those electrons. All right, let's think of hydrocarbons. Hydrocarbons contain only carbon and hydrogen. Which of these hydrocarbons, C2H6 ethane or C4H10 butane, has the higher boiling point? Think about it. So we're comparing within a class of chemicals or a class of compounds. So there's a way that we can compare their intermolecular forces. Intermolecular forces determine or play a role in boiling point. So our strength of our our intermolecular forces determines or influences boiling point. It also affects melting point, but we're thinking about boiling point here. What's going to cause us to have a higher boiling point? Stronger forces or weaker forces? So higher boiling point, what we're looking for, higher British Petroleum, comes from stronger intermolecular forces. Since we're looking for the higher boiling point, right, we're looking for the one that has the stronger intermolecular forces. We only know about one force, which is dispersion forces. Which of these two is going to have stronger dispersion forces? C4H10 has stronger dispersion forces. And we know that it has stronger dispersion forces because it's got a higher molar mass and we're comparing within the same class of chemicals. It has more electrons, higher molar mass, so it's going to have the stronger dispersion forces. This wouldn't work if we were comparing different types of chemicals. Questions about dispersion forces? Our next force is the dipole-dipole force. And the dipole-dipole force exists in polar molecules. So hopefully you remember polar molecules from the end of chapter 7, or towards the end of chapter 7. Polar molecules have permanent dipoles. So with our dispersion forces, we had temporary dipoles, temporary partial positive, partial negative forces. And because of them being temporary, let's see, our dispersion dipoles are temporary. Since they are temporary and also weak, permanent forces are going to be stronger, right? They're always there. They're never going to go away. So just on average, we can think of them as being stronger than our dispersion dipoles. Those partial positive, partial negatives being the dipoles. So one of the chemicals that we looked at was this one. And we know that oxygen has a stronger electronegativity value, a higher electronegativity value. It's like 3.5. So we get a partial negative charge over by the oxygen compared to the carbon. Carbon having an electronegativity value of like 2.5. So we get a permanent dipole that forms across this molecule. We're always going to have partial negative charge on the oxygen because it's pulling these electrons from the double bond. It's pulling them a little bit closer to itself. So carbon in reality has a little bit fewer, a little bit less electron density, and so it's partial positive. It doesn't have all the electrons that it wants or should have. And because these are stronger forces, because they're around for longer, they're there all the time, that increases the melting point and boiling point relative to our nonpolar molecules. So here's that same molecule. We've got it stacked up. So these partial positive and partial negative ends are going to find each other just like really weak magnets. You get a bunch of magnets together, you like shake them around, they'll all eventually clump up. That's kind of what these do, except the forces are much weaker in the case of these molecules. Again, it's the permanent part that makes them much stronger. So these are stronger than dispersion forces. We can compare the effect of being polar versus nonpolar for two compounds that have a similar mass. So formaldehyde, the one that we were looking at, and ethane, C2H6, showed up in our example problem. They have a very similar molar mass. They're almost identical. So a molar mass of 30, a molar mass of 30.1. So we wouldn't expect to see a whole big difference in just dispersion forces alone. Formaldehyde is polar, so it has dispersion forces and dipole-dipole forces. Ethane is nonpolar. Since it's nonpolar, it doesn't have dipole-dipole forces. It only has dispersion forces. So we're pretty much just looking at what's the difference between having dipole-dipole forces versus not having dipole-dipole forces. And the way we're comparing that is with our boiling point and our melting point. So our boiling point for formaldehyde is about negative 20 degrees Celsius. Our boiling point for ethane that doesn't have dipole-dipole forces is almost negative 90. So we've got a difference in about a 70°C increase in our boiling point just because of having the dipole-dipole forces. Our melting point is an 80°C difference just because of having those dipole-dipole forces. So it takes an additional 80°C or 70°C, depending on which one you're looking at, to overcome those intermolecular forces, overcome those atoms and molecules sticking together. Questions or confusion about that? Polarity also affects miscibility, which we've talked about before. It's sort of mixability. It's not exactly the same, but we can think of it as mixability. How mixable the two things are, how well they'll dissolve into each other. So miscibility, the ability of a liquid or a solid to mix into a liquid without separating out into two phases. Phases here being layers. Generally, the rule is that polar liquids, things that have dipole-dipole forces, are miscible with other polar liquids. They're not miscible, they're immiscible with nonpolar liquids. So polar, things like water and ethanol. So an example of those two mixed together, right, vodka. If you've seen vodka, it's clear it's one single layer all the way through because the ethanol and the water are miscible. They're both polar. Things that are nonpolar include things like gas and oils. And gas and oils will often be miscible with each other. Sometimes if you get really bad grease on like car parts, you can wash them off with like hexanes or some other nonpolar solvents. Those will take them off very easily, and then you don't have to use water and soap, which can be bad for metal parts. If you mix together, or if you put oil and water together, oil is nonpolar, water is polar, those will not mix into a single layer. So think of like vinaigrette salad dressings. You always have to shake them up before you use them because the oil will separate out to the top and the water part and a lot of the flavor and vinegar and stuff will be on the bottom. So a lot of salad dressings you have to mix before you shake them because they won't be in one single layer. The way that you can overcome that, like if you have oily hands or oil stains on your clothes, is that you add soap and that acts as an intermediary and gets the two to mix together. Some examples: chloroform and water don't mix. We saw that in one of our first labs when we were mixing up the two layers. The chloroform is more dense than the water, and so the chloroform sinks to the bottom, the water sits on top. No matter how many times you shake it, it's not going to mix. Oil and water don't mix. Oil is less dense than water, and so it floats on top. And then here's an image of the famous Deepwater Horizon oil spill, and you can see the oil all over the Mississippi Delta. It also doesn't mix and causes all sorts of other issues. So if we want to determine whether a molecule is polar, we've got the Book's method. Figure out if you've got polar bonds. Determine whether those bonds add together to form a net dipole moment. So thinking about like arrows and directions and other things like that. We also have the nonpolar express. If we have no lone pairs on our central atom, like CH4, no lone pairs, on our carbon, and all the bonds are identical or have the same electronegativity, then it's nonpolar. So CH4 is nonpolar. Meets both of those conditions. If, however, we have something that has a polar bond, if it has polar bonds, and fails either condition, it is polar. So an example of this would be ammonia. And our Lewis structure for ammonia looks like this. So ammonia has a lone pair on the central atom. It forms the trigonal pyramidal geometry. And the nitrogen-hydrogen bond is polar. So this is a polar molecule that will also dissolve in water. It's one of the active ingredients in Windex. Questions about polarities? Some of this is sort of review from 2 chapters ago. Okay, dipole-dipole forces. Consider these molecules, determine whether they have dipole-dipole forces. Go ahead and add in the electronegativity values in case you don't have your table with you. And here come the Lewis structures. Go ahead and put in all the lone pairs just for fun. All right, CF4. We have polar bonds. Right, our difference between carbon and fluorine is 1.5. That's pretty strongly polar. So we definitely have polar bonds, so we do need to check if it's got dipole-dipole forces. If it didn't have any polar bonds at all, then we wouldn't worry about it. So these polar bonds, we'll go through our nonpolar express method. Do we have lone pairs on the central atom? Or rather, do we have no lone pairs on the central atom? Yes, we have no lone pairs on the central atom. Okay, no lone pairs on carbon, check. Are all of our bonds the same or the same difference in electronegativity? Yes, they are. So that means that CF4 is nonpolar. Since it's nonpolar, it doesn't have dipole-dipole forces. No designated driver forces. No crafting store forces. So that's CF4. We also have CH3Br. Does CH3Br have any lone pairs on the central atom? No, no lone pairs on carbon. Are all the bonds the same? All bonds are not the same. So this one is actually going to be, or we would expect it to be polar and have dipole-dipole forces. The reason that it's polar, even though the difference in electronegativity isn't very strong, or the reason we'd expect it to be polar, this 0.3 difference and this 0.4 difference, so between the bromine and the carbon, is a 0.3 difference in favor of the bromine. For the carbon versus the hydrogen, the carbon is winning out a little bit. And because of the way that this is going to be arranged, we wanted to draw out all of our arrows. Do a wedge since this hydrogen's coming out, and dashed because that hydrogen is going away. On the bromine bond, we're going to have a slight favor, more electronegative towards the bromine. And for each of these bonds between the carbon and the hydrogen, it's going to be partially positive. So these arrows are adding up. So we would expect to have partial negative up by the bromine and a partial positive down towards the hydrogens. The takeaway, though, it's polar. It has dipole-dipole forces. How about HCl? Is HCl a polar molecule? Yes. The reason that HCl is a polar molecule, we have one bond. It's between hydrogen, which has an electronegativity value of 2.1. Chlorine has a 3.0. Our difference in electronegativity is 0.9. That puts us in the polar range. Whoa. Not that big. 0.9. There's nothing to cancel out that force. Right? It's just chlorine and hydrogen. Chlorine's winning here. Questions about dipole-dipole forces? Pop quiz. What type of chemicals have dispersion forces? If you said all chemicals, you are correct. It is all chemicals. Anything that has electrons has dispersion forces. What kind of molecules, what kind of compounds have dipole-dipole forces? Polar molecules have dipole-dipole forces. And then our next force, hydrogen bonding. This is our third force. This is our strongest force yet. Strongest so far. Polar molecules, so things that have dipole-dipole forces, that have a specific circumstance. They have hydrogen atoms bonded directly to fluorine, oxygen, or nitrogen, also have hydrogen bonding. So fluorine to hydrogen, oxygen to hydrogen, nitrogen to hydrogen. If we have these bonds happening, then we also have hydrogen bonding intermolecular forces. This is a super dipole-dipole force. It's stronger than regular dipole-dipole forces. There's some reasons why this is the case. If we look at our periodic table, we find fluorine, oxygen, and nitrogen. Fluorine, oxygen, nitrogen, right? They're all up in this row 2. Those are going to be very small in terms of their size, small atomic size. They also have a large electronegativity values, relatively. If you remember our mnemonic device Fonkel-Brick ship, right? FON are the first 3 on that list. Fluorine has a 4, oxygen has a 3.5, nitrogen has a 3.0. Big difference in electronegativity in small size means that we can get these 2 atoms close to each other. Hydrogen and fluorine will get much closer to each other than hydrogen and chlorine, since chlorine is bigger. So think of this as if we've got 2 magnets, since they're really small and really strong magnets, we can get them super close to each other, almost touching. That force between those 2 magnets is going to be a lot stronger than if you move the magnets further apart, which would be like if we used anything bigger than fluorine, oxygen, or nitrogen. So these are the 3 elements. If they're bonded to hydrogen directly, then we can get hydrogen bonding. Hydrogen bonds are not just bonds with hydrogen. Tons of things have bonds with hydrogen because hydrogen's in them. This is a particular case of hydrogen bonded to something else. Our hydrogen bonds is an intermolecular force. It occurs between molecules. It's responsible for keeping our DNA together. Covalent bonds occur between atoms within the same molecule. They're not covalent bonds. They're also much weaker. They're only 2 to 5% the strength of a covalent bond. But they're way stronger than regular dipole-dipole forces and super, super stronger than our dispersion forces. So looking at HF, we've got hydrogen and fluorine. When things are bonded together, we'll often represent them as like their orbs overlapping. This is one way we can think of them and look at them. Because of the big electronegativity difference between these 2, fluorine is hogging the electrons. It's got this partial negative charge. It's stronger than if it was something that's bigger. So if we had chlorine here, this partial wouldn't be as big. And that can attract the partial positive of the hydrogen next to it. So they line up the same way as dipole-dipole forces. Because they're just a super dipole-dipole force. Polar molecules line up the same way, but these are stronger. So stronger than in a normal polar molecule. Methanol, wood grain alcohol, has hydrogen bonding. It's got oxygen directly bonded to a hydrogen, and so it can engage in hydrogen bonding. So this has dispersion forces, dipole-dipole, and hydrogen bonding. Generally, we only care about the strongest of the forces, so hydrogen bonding is the one that we would care about here. And to show you the power of hydrogen bonding, we've got a comparison between 2 similar molecules. So we're looking at ethane. Ethane has dispersion forces. We saw that earlier. Methanol has hydrogen bonding. They have similar molar masses, so we know their dispersion forces are going to be approximately the same strength. the difference in their boiling points and melting points is what tells the real story here. So we saw earlier, I think it was about -20 for formaldehyde for our boiling point. Now we've got a boiling point of 65 degrees Celsius. So we've got a difference of like 170. If I'm doing my math correctly, that's like 175 degrees Celsius. So almost double the difference between the freezing point and the boiling point of water. And we've got about an 80 degrees Celsius difference, 80 to 90 degrees Celsius difference, 85, for our difference between our melting and our boiling points, just by having the added strength of hydrogen bonding. Hydrogen bonding also occurs in water. This is part of the reason that we're alive. So water, because it's just oxygen and hydrogen, it gets extra hydrogen bonding. And that's why water has such a high boiling point despite being a very small molecule. And as I mentioned earlier, hydrogen bonding is what keeps our DNA strands together. So we have that to thank for being alive. Questions about our dispersion forces, dipole-dipole forces, or hydrogen bonding? Okay, then we'll pick up here next week.